Hi everyone, we're on question 15 now of paper 1 and for Edexcel for A-Level 2022, and we've got a what's called a differentiation optimization question, and I really cannot emphasize enough how important these kinds of questions are. They come up quite frequently. They're a favorite across a number of exam boards who like them because they know that it really separates students well in terms of their understanding. So very, very popular with examiners. And invariably, it's worth a lot of marks. I've seen this question be worth up to 15 marks. This particular one's worth 10 marks, but I've seen them worth a lot more than that. So it's super important to know how to do this particular kind of question. Okay, so what does it say? It says a company makes toys for children. Figure 5 shows the design for a solid toy that looks like a piece of cheese. The toy is modelled so that the face ABC is a sector of a circle of radius r and centre A. The angle BAC is 0.8 radians. The faces ABC and DEF are congruent. The edges AD, CF, BE are perpendicular to the faces ABC and DEF. The edges AD, CF, and BE have the length h, excuse me, and it says given that the volume of the toy is 240 centimeters cubed, show that the surface area of the toy is given by that equation there. Now, in terms of the approach for this question, okay, what they're going to do is they're going to give you maybe the volume and then ask you to find an expression for the surface area, which is what we've got in this particular situation here. So the key is there's two steps. Step 1, you need to write an expression for the volume, okay, which will be in terms of at least two variables, in this case r and h. Step 2, you then need to write an expression for the surface area, which will also be in terms of those same two variables r and h. So you write an expression for the volume, you write an expression for the surface area. Now, because they've told you that the volume is equal to some particular amount, in this case 240, you can then rearrange it to make either that one or that one the subject and sub in. Now, if we look at the equation that we've got aiming for here, we're aiming for S is equal to 0.8 r squared plus 1680 over r. You'll notice that there is no h in this equation. So we've got an expression here for volume. It has r in and it has h. We have an expression for surface area. It has r in and it has h. So we need to rearrange this one to make h the subject and then replace it in this equation, okay? So I'm going to do that. How am I going to do that? I'm going to times the 240 by 2, so it's going to go to 480, and I'm going to divide by 0.8 r squared. So when I rearrange this to make h the subject, it's going to say h is equal to 480 over 0.8 r squared. So a rearranged version of that now gets subbed into there. And now you'll observe that everything is in terms of just the one variable r. Okay, so let's tidy this up now. So 480 over 0.8 times by 2.8 just so happens to be 1680, which is super encouraging. We've got here this r cancels with the squared, just leaving us the r in the denominator. And then we had our 0.8 r squared. Okay. Oh yeah, I need to describe where these formulas have come from. So the first formula, where's it come from? So it is a prism, and the volume of a prism is going to be the area of the cross-section times the height. So the cross-section is a sector of a circle, and remember we're in radians here because they tell us in the question it's in radians. So therefore the area of that sector is a half r squared theta. The volume of a prism is the area of the cross-section times the height, and the height is h. So that's our expression for our volume, which we're told is 240. Now the surface area, which remember is as if you were going to paint the outside of the shape, we've got two of these sectors like this. We've got two rectangles and we've got one curved face at the end. So there's 2 times by a half r squared theta. So 2 of those. We've got 2 of these rectangles, which are r times by h. And then if you remember, the arc length is equal to r theta. So the arc length from here, from C to B, is r theta. So r times by 0.8 times by h is going to be the surface area of the curved bit at the end. So bringing all of that together, we have 0.8r² there, so that's this bit. And then we have 2r times h, so 2r times h, and we have 0.8 times r times h, so 0.8 times r times h. So that's where the expression for the surface area came from. And then we simply rearrange this one, because this is the one that they gave us the volume for, and subbed it in to get the expression that we need. Now I know it seems quite fiddly, and it's usually worth about 4 marks, sometimes 5 marks. And in my opinion, it's always this part A of the question that's always the trickiest. It's always the bit that takes the longest, has the most algebraic manipulation. Usually the part B and part C, which are worth at least the same amount of marks, are dramatically more straightforward. But that's our part A done, okay? So let's just review the steps again. Find an expression for the volume, find an expression for the surface area. They're usually in terms of 2 variables, so you eliminate one of the variables to get the expression that the question gives you. The only variant of this question that sometimes comes up is, instead of it being volume and surface area, sometimes they do perimeter and area, but the same procedure applies. You find an expression for the perimeter, you find an expression for the area, and you sub one into the other. Okay, super important. Right, now part B. So it says, use algebraic differentiation to find the radius for which S has a stationary point. So basically we just need to find what the maximum surface area is going to be. So we need to differentiate our expression, set it equal to 0, which you can see here, ds by dr equals 0. So let's differentiate this expression. So we're going to, with differentiating with respect to r, so we're going to have 2 times 0.8 there. This is same as 1680r to the minus 1. So 1680r to the minus 1. So we times by the power that's there and lower the power by 1. So that becomes minus 1680 over r squared. We're setting this equal to 0, and we need to solve it for r. So we're going to take this bit over to the right hand side, giving us 1.6r equals 1680 over r squared, times everything by r squared, divide by 1.6, okay? And that gives us that r cubed is equal to 1050. We take the cube root of that, the cube root of 1050 gives us that r is equal to 10.163, which is 10.2, to 3 significant figures. So usually that second bit is like dramatically easier. It's usually like just differentiate it, set it equal to 0, and solve for r. And it's worth the same amount of marks as part A. And then finally now it says, prove by further differentiation that this value of r gives the minimum surface area of the toy. So in order to prove a maximum or a minimum, we need to just differentiate a second time, okay? So we're going to find now d2 s by dr squared. So remember, our ds by dr was 1.6r minus 1680 over r squared. So when we differentiate this again with respect to r, that becomes 1.6. And then we're going to have plus 3360 over r cubed, because this is the same as 1680r to the minus 2. So you times by the power that's there, so that becomes a plus, lower the power by 1. Okay, so now when we put in our value of r, which was 10.2, we find that we get 4.77, which is greater than 0. And this is the condition that's required for something to be a minimum. So when we've differentiated a second time, put in the value of the radius that was at the turning point, we find it's greater than 0, which means that this is a minimum. Okay, so very, very, very important question. And there is an amazing source. There's a free website here, which I can just show you. If I just go on to yesterday's maths exam is an amazing free website here. So if we go to yesterday's maths exam, just so I can show you, it's a really good website. I can't recommend this enough. So you go to A-level Edexcel. It's actually an AS topic, even though it's here in A-level. Scroll down on this website, and if you go to here where it says differentiation optimization, here then the creator of this website has compiled all of the questions on this topic for you. So there's absolutely loads of questions here that you could use to practice and make sure that you've honed your skills on this particular question. Fantastic free resource that. One of my students made me aware of it a couple of years ago, and all thanks to the person who created that website. It's super useful. Okay, great. Well, if you're not a subscriber of the channel, if you could become a subscriber, that would be fabulous. That'll help me to keep on making videos that you'll find helpful. And thank you for watching, and I'll hopefully see you in the next video.